Okay, thanks. So it's wonderful to be here, back in sunny Southern California, or California, right? I did my PhD work in Southern California. It's nice to be back in the sun because now I'm up in Seattle, which is a little bit rainier, turns out. So you might also know that right here in Berkeley, we're sitting right on top of the Hayward Fault line. So let's just imagine for a second this room started shaking, right? Major earthquake event happens. Think about after that shaking stopped, what would you do? Okay? So for many of us, we might be thinking, okay, what just happened? Right? If you have never experienced an earthquake before. You might also think, am I still in danger? Do I need to evacuate this building? Are my family and friends okay? Right? All of these kinds of questions come up during crisis events. Right? And it's actually very well established in the social sciences that what do people do to answer these questions? They turn to their social networks. Right, so you might turn to your neighbor, the person sitting next to you, discuss what happened, try to think about what to do next. You might call family and friends. Right? You might get on social media. Right? So you might open up Twitter to see what other folks are saying about what just happened. So this is what I want to talk about today. Social behavior during crisis events. And what's really interesting about this context is that the social behavior unfolds in conditions of extreme stress, right? Very disrupted settings, non-routine situations. You don't experience a lot of these in your lifetime. So the decisions that you make in this context, right, and the actions that you take can quite literally have life-altering consequences. So this is our topic for today. And in line with many of the other things we've heard about throughout the day today, I'm going to argue that we can better understand this kind of social behavior during crisis by making use of digital trace data, right, of the things that we do on the internet. So hopefully what we learn in this endeavor will not only help us improve response and recovery strategies, but it will allow us to reduce human losses, economic losses, and potentially mitigate these kind of long-standing damage that happens to affected communities. Okay, so sociologists have been studying this kind of social interaction during crisis for a really long time. Right? And we don't think of crisis as a very narrow thing. We actually think very broadly about crisis. So this can be natural disasters. It can be civil or political unrest. It can be acts of terrorism. Sort of these all fall under our umbrella of crisis. So today I'm going to talk about a few different kinds of crises. Now, crises are really interesting because they're shocks to the social system. Right? So major exogenous things happen, and they reveal core behavioral patterns. They also reveal the social factors that might constrain those kind of behaviors. And so some of the key behaviors that happen during crisis events include things like information seeking, exchange, dissemination. Right? Those are sort of oftentimes the first questions you think about after disaster events. Right? Rumoring is a slightly more complex phenomenon where people are trying to make sense of, right, collectively make sense of what just happened and what's going on. Things like coordination and improvisation are also very prevalent, right, because this is a non-routine situation and we have to respond to it, individuals and groups and organizations and everybody together. And finally, mass convergence describes the tendency for people, information, and materials to all converge on the physical area of impact. Right? Contrary to sort of some assumptions that people make, normally we don't see mass sort of like people fleeing from disasters. You see a lot of convergence. Okay, so I'm going to focus on two of these things today. We don't have time to talk about them all, which are rumoring and mass convergence of attention in particular. So we're going to discuss the ways in which digital data and computational techniques, right, computational social science and data science can help us to better understand these phenomena and the consequences of these phenomena. So let's look at rumoring behavior first. Right, so as social scientists, we don't actually restrict our definition of rumor to just mean false information, things of doubtful truth. We actually think very broadly about what rumor is. And for us, rumor is going to simply be stories that are unverified at the time that they're being talked about. Right? so this is what we think about as rumors. And early studies of rumoring that came out of the social sciences are very theoretical driven because it's hard to get data on rumors, right? Think about trying to go into a crisis-affected area. People are going to have better things to do than answer your survey questions about did they hear this information, who did they hear it from, did they pass it along, and so on. Okay? So some examples of this kind of classic theory-driven work are Allport and Postman's work that is sort of a classic in this area, but they sort of theorize, hypothesize that rumor spread is determined by the importance of the information, the uncertainty surrounding that information, and the information, how that information might suggest behavioral changes, right? What you might do. So we can actually test some of these theories using behavioral trace data. And what's interesting about rumoring is that some people think about rumoring as a bad thing, right? And rumoring actually serves a very particular social function during these kind of disrupted settings where it allows people to alleviate their anxiety and then actually make decisions and take actions in the face of extreme uncertainty. Because it allows them to improvise news, right? And this is the case when official channels might be unavailable or just not very timely, right? So people have to make sense of things together. Okay, so I'm going to talk about the ways that we try to understanding this collective sense-making process of rumoring. And this is work that spans a number of projects and a number of collaborations, but what I want to focus on today is a particular portion of this project that has two aims, right? So our aims are twofold. First, we want to better understand the social dynamics of this process of rumoring by mapping patterns of rumoring over time and looking specifically at how people engage with this kind of rumor-related content online. And our second aim is to actually use crowd correction, right? So the tendency for people to deny or challenge information to identify misinformation, right? By that I mean false rumors. Okay? So if we can do this, then potentially we can help out, the poor unsuspecting soul who sees this tweet that was posted during Hurricane Sandy and actually thinks that sharks are, roaming the neighborhoods of Manhattan and New Jersey, and they decide, okay, I can't go outside, right? I might get eaten by a shark. Okay. So our end goal is ultimately to help with emergency management. And emergency responders are actually very quick to cite the potential for rampant misinformation online as one of the major reasons that they're very reluctant to fully incorporate social media into disaster recovery management strategies. Right? But if we can better understand how misinformation flows through populations and these kind of online publics, then we can potentially give them guidelines to combat this very detrimental misinformation that can really affect the safety of communities. Okay, so how do we actually go about doing this? I want to spend a little bit of time talking about the process involved with these kind of computational social science studies, because I think this is actually one area that tends to get underemphasized, and it's not easy, right? So first thing we have to do is be able to collect data. Right? We want to collect data on crisis-related social media posts. We want to then identify rumors within that content, so rumors that are being talked about at that time. Then we have to think about actually defining the boundaries of those rumors, right? Labeling them, because we want to understand how people engage with social media content. Right? This means we manually read every one of these tweets, right, and code it. And then finally, we get to a point where we can actually analyze data, right? So we have a bunch of data, and we can think about analyzing that data with whatever techniques we're going to use to address our aims. Okay? So I want to talk specifically about some of the challenges that arise, because at every point in this process, you encounter challenges, right? And we have to deal with them. Our strategy has been to incorporate statistical learning methods to augment qualitative approaches. Right? So we have both ends of the spectrum here. Okay, so we have to first collect data. And the choices that we make about sampling digital data are extremely important, right? Because they can have a very large effect on the analysis that you do. These kind of choices define what you include in the data set you're going to analyze, and equally important, they define what's excluded. Okay? So we identify a crisis event. We have to think about making very rapid decisions. Oops, did I go too far? Sorry. We have to make very rapid decisions about what search terms to use to collect data. Right? And we do this with the Twitter API. And you have to do this in an information space that's evolving over time. Okay, so not an easy problem. And at UW, we have a team of student researchers who are sort of monitoring breaking events, and then they're learning how to curate these kind of keyword sets that we use to sample data. And all of this is built on a huge sort of platform software that we wrote to query and access and archive data from the Twitter API. Okay, so we have data. Now we have to identify rumor stories. And importantly, we have to define the boundaries of those stories. Okay, so this can be really challenging because stories aren't just the same over time, right? They change, they permute, they evolve. And we need to understand where one rumor ends and the next one begins, right? Not the most straightforward thing out there. So we have a story. Let's say we can define it. We then have to think about all the data we have in our data sets that's related to that story. So identify all these relevant tweets in our case, and we have to do this with both high precision and high recall. Right? If we have too much noise, and then we waste the resources of our human coders. Right? We're just asking them to code a bunch of nonsense. And if we have too many missing cases, that means we're potentially neglecting a lot of these crowd corrections that we're really interested in, because the crowd corrections tend to use non-standard language. They sometimes even lack a very explicit reference to the rumor itself. Okay, so let's say we have some data, it's related to a rumor. Then we go through and we manually read every tweet and we code it. Right? So we have a coding scheme that we've developed that thinks about annotating every one of these posts with their stance towards the rumor, as well as other elements. And we have to train our coders to be able to do this reliably across rumor events and across different crisis events. So obviously this task is very resource intensive. Right? I can only ask undergraduates to read and code so many tweets. So this is one area where we incorporate a lot of computational techniques as well. So we use machine learning methods to also automatically try to classify each of these messages. Right? And this is one area where we have incorporated data science techniques with really great effects. So here's a recent study that we did that looks at data from rumors that happened during the 2014 hostage crisis in Sydney, Australia. So what happened during this event is a gunman took control of a cafe, took hostages. There were lots of rumors going on because there were rumors of involvement by ISIS and all kinds of things that happened. This event eventually ended when police stormed the cafe, the gunman was killed, and some of the hostages were killed as well. So across multiple rumors that we've identified in this data, both true rumors and false rumors, we manually code these tweets as affirming the rumor or denying the rumor. Right, so I just want to talk really quickly about this distinction between affirm and deny. We also have neutral tweets. We also code for other kinds of elements, but in the interest of time, I'm not going to talk too much about all of those other things. So we code things as affirm or deny. We have a simple classification problem here, and all of this manually coded data becomes our training data. Okay? So then we do some experiments with various statistical models, right? So we try things like logistic regression, naive Bayes, random forest models, and we do pretty well. Okay, so we extract a bunch of features based on the tweet characteristics, text elements, and user characteristics, like things like n-grams and parts of speech and so on. And we can achieve an accuracy of around 88%, right, across our, on average across our different models. So this is pretty good if you compare it with a baseline of 66%, which is just if you predict the dominant category. Right, so not bad. And one of the things that's really interesting about this is because you can feed the machine learning algorithm as many tweets as you want, right? It allows us to scale up our manual coding. Okay, so not only can we then apply these annotation approaches to very high volume rumors, but it also allows us to use prior observations to inform the coding of new data, right? Things we haven't seen yet. Now, there's lots of important questions to be asked about this kind of automated coding. Most importantly, right, when we get to our fourth box over here, when we want to analyze data for whatever our quantity of interest is going to be, we want to ask whether that human coding and that machine coding lead to the same inferences about that quantity. Right? So this is a great question for future work. Right? We'll see what happens. Okay, so I want to talk a little bit about the ways that we analyze rumoring. There are many ways we can do this, and we do approach this from many different angles. But I'm not going to talk about all of them today. What I do want to talk about is just trying to understand rumor prevalence. Right? So many previous studies of rumor also look at prevalence. And they tend to measure prevalence by just the number of messages that we see in the environment. Right? So volume. And this is data that comes from that same Sydney event. This is a rumor about police raids that were supposedly going on during the crisis. And you can see the volume signature in these sort of light time series lines here. Okay? So, but if we actually think back to many of the social theories of rumoring, right, from the past, then they're not really about volume of messages. Right? They're about number of people who have seen those messages. So we also want to estimate the size of the exposed population. And we can try to do that by just weighing each of our messages by estimates of the audience for that particular author. Right, so we do that, and exposure is represented in these blocked bars here. So if you can't see it exactly, the bar is made up of a bunch of little blocks. Right, and the size of those blocks is the size of the audience for that one tweet. Okay. So we have volume and we have exposure. And the first thing you see, hopefully, in this picture is that they look different. Right? So if you were going to measure prevalence with volume and you were going to measure prevalence with the size of the exposed population, these trends wouldn't match up. Right? So you can see places here where there's a small spike in volume and there's a giant spike in exposure. Right? Or you can see other places where there's spikes in volume but not very much exposure. So what's going on? Well, I find it helpful sometimes to look at very concrete examples. So let's take a look. Here's one example that can help us understand what's going on. So as I said, this rumor is about the Australian Federal Police conducting raids in a particular neighborhood within Sydney. And what happened at this particular point in time here, that's labeled 2, was this tweet. Okay, so the Australian Federal Police media account posts this message that says, these rumors are wrong. Right? This isn't actually happening. And if we dig into this case a little bit more in detail, we see that this account had a few thousand followers at the time. But if we estimate the derivative volume that they exposed people to this content, we find that almost 2 million users could have been exposed to this particular message. Okay? How did this happen? People passed this message on. Okay? So the network structure is really important to the diffusion process here. And across all of the rumors in our data and many different events that we've studied, we see that both the network features of the people who are involved in these conversations, as well as the content of the messages they post, both of these two things interact to structure the diffusion process and the rumor dynamics. Yeah, Duncan.
Which things are we comparing with the left-hand y-axis, and which things are...
So number of tweets is volume, and the bars are exposure.
So number of tweets is the lines?
Yes, these ones.
So the lines are against the right-hand y-axis, and the bars are against the x.
Yeah, I don't care so much about the numbers, and actually I hate putting two y-axes on one plot, but I just wanted to show you that the two things don't track exactly. Yeah. Okay, so we could kind of put this together, and one thing that we found helpful is to actually construct this kind of typology for identifying these kind of important points within the rumor signature. Okay, so I'm going to talk about each of these sort of four 4 typologies, characteristics of things, because we've found them helpful in conceptualizing how things happen over time. Okay, so we're going to start with giants here, and we know that some social media users have really large audiences, right? Think Justin Bieber. Right, so he posts a particular message, it gets really picked up by people, they respond to it, they pass it along, and it just kind of leads to this giant cascade. Right? They're really giants within the conversation. So, but we also know that not all messages from these highly visible people lead to these giant cascades. Okay, so we also have people where they have a large audience, but their tweets kind of fizzle. Right? Nothing really happens with them. Right, and likewise, those with small audiences can also make waves in this kind of conversation. So we do see messages that start from very less visible users, right? But they get picked up by the crowd and they keep moving on and on and on until they can dominate the conversation, right? Just like snowballs that are rolling down a hill. And finally, we just have a bunch of messages from a bunch of people that nobody cares about, and this is kind of the babble of all this kind of noise within social media. So, one of the things that this typology emphasizes, and we found it helpful to think about rumoring dynamics, is the fact that retransmission of content is key. Okay? So people have to pass things along. So what do people decide to pass on? Right? Open question. We're working on it. Right? How do they react differently to different kinds of messages, or even the way that content is designed? Right? If you put things in all caps, are they going to pass it along more than if you don't? And importantly, how fast do these kind of rumors spread during crisis events? Now, this is a particularly interesting question for crisis because often the information is extremely time sensitive. Right? It doesn't do any good to get an evacuation notice after the event has already concluded. Okay? So we are going to compare the speed of retransmission for these kind of rumor-related messages because we want to know if denials can actually outpace affirmations. Right? If you have a fast reaction to content, can that denial spread faster on the social network than these affirmations of content? So we do that. And what I'm comparing here are waiting times, median waiting times. So the time between when the original message was posted and each instance of retransmission of that message. Okay, so the top figure here shows random tweets, crisis-related tweets, but not rumor ones, and then rumor tweets. Okay, so what you see is random has really sort of on average long waiting times. People tend to respond to crisis information faster, and they tend to respond to rumors even faster. Okay? And on the bottom plot here, I'm just showing for those rumor tweets, affirm versus deny tweets. Right? So what do we see? The denials have a shorter waiting time than affirmations. Right, this is just a figure, but obviously we do this with a statistical model, and we actually show they have a statistically significantly shorter waiting time. Yes?
What is a crisis tweet if it's not a rumor?
So it can just be like about the event. So in particular, let's say I showed you that rumor before about police raids that are going on. If I were to just post a tweet that says, there's a hostage situation going on at this cafe, that's not about the rumor, but it is about the event.
Why isn't that a rumor?
Because, well, it's a good question. At that point, it's confirmed that this event is going on. Right, so by our definition of rumor, it doesn't hold. But it's also not part of one of the specific rumors we're looking at in this case. Yeah, good question. OK, so retransmission speed. So we've learned a lot about rumoring over the course of this project. Just a couple things to think about before I talk about mass convergence. Rumoring is a very natural social behavior, right? And it often emerges during crisis events because of the heightened level of uncertainty that's going on during those situations. Right? It's really important to understand how rumors spread and how people engage with rumor content for crisis management. Right? We have seen that online crowds can actually be effective at making sense of uncertain information, and they can be good at correcting misinformation as well. Okay? So we want to look at rumors not only in terms of volume, which is the typical way that things are done, but also in terms of exposure. And finally, we need to better understand these propagation mechanisms, right? Things like retransmission. And we need to know that they can potentially have different impacts online than they would in word of mouth, right? A great example of this is distortion, right? A lot of the early work on rumoring was really focused on distortion because, think about the telephone game. I say something to you, you say something to somebody else. By the time it gets to the end, it might look completely different. Right? This is a very different process than Twitter, where I click a button and the same message gets posted and sent to my followers. Right? So we need to reformulate and extend some of our theories to think about rumoring. Okay, so I want to spend the latter part of my time today thinking about another really important social behavior, which is mass convergence. Okay, just like rumoring, mass convergence, specifically of attention, happens a lot during crisis events. And this is a phenomenon where individuals and organizations can experience extremely drastic changes in their personal network structure. Okay, so mass convergence happens offline as well. And we see that people and information and materials all converge to the physical, geographic area of impact following disasters. And what's really interesting about this particular behavior is that it represents this extreme departure from what's normal social behavior, right? It's not every day you sort of drop everything and rush to help somebody at a particular crisis event. Right? You might fly across the country or across the world to go help out in these kinds of situations. So convergence behavior is now mirrored, and I would argue potentially enhanced or extended in online contexts. So just look back at the most recent crisis event. Right? We have a global audience that turns to social media to follow what's going on with that disaster. We see digital volunteers mobilized to coordinate relief efforts and to help raise, funds and money and supplies for the people who are affected by disasters. Right? And all of this happens online. Right? There are many new modes of public participation in emergency management. So if you're not convinced yet, let me show you a couple examples. So we see mass convergence all over the place. So here are some data and some figures from a recent study that we did that looks at the information behaviors of emergency responders. Okay, what do they say on Twitter? What do they do in these online environments? So we wanted to estimate sort of general conversation that they were posting. So we have a set of nationally representative emergency responders, all of their tweets for the past 4 years. And we fit a basic LDA topic model on this, and we compare behaviors across accounts, and then we look to see what do they say on days when there's no major disaster event in the US, and what do they say on days when there is a major disaster event. Right? So hopefully I've already given away the punchline, right? We see convergence. Right? So if you look at these two figures, what's going on? Well, all of these accounts start talking about the same thing. Right? They start talking about the disaster. So this isn't necessarily surprising, but we see it very clearly. Right? So if you were confused about what's going on in this plot, this is just a multi-dimensional scaling of the similarity between accounts. Right? So the physical distance between points here is a representation of their similarity, or likewise distance in each one of our points is an account. Okay, we also see mass convergence of attention in social networks. And so here is some data where we're just looking at the number of followers of a particular emergency management account. Right? So same set of counts I talked about in the past. And what happens here during the Boston Marathon bombing is the Massachusetts Emergency Management Agency has orders of magnitude change in the number of people paying attention to them on Twitter. Right? Same thing happens for New Jersey Governor Chris Christie, right, during Hurricane Sandy. So in the language of social networks, what happens here? Well, there's really, really major changes in people's personal networks. Right? The size of those networks, the number of connections, their degree changes. Crazy changes in the span of a few hours or potentially a few days. So this kind of mass convergence of attention can be a really great opportunity, right? It can facilitate information diffusion. It gives you direct access to potentially more people, maybe members of that affected community. And it also gives you indirect access to a lot more people because you just have a lot more ties. Right? It can also have very large costs. Okay? Any mistakes you make are very much made in the public eye. Okay? So over and over again in our studies, we see that local emergency responders are often the target for this kind of convergence of attention. Right? So these tiny little accounts that nobody's ever heard of before all of a sudden becomes this major celebrity-like figure during these crisis contexts. Okay, so one of our newest projects in this area seeks to characterize these kind of degree dynamics. All right, so first thing we want to do is look at baseline growth over time. Right, you saw those plots that I just showed. There tends to be this sort of gradual increase in the number of followers people have. And our preliminary analysis shows that that can be consistent across these organizations. Right? Second thing we want to do is be able to predict the incidence and the magnitude of these convergence events. Right? And it looks like we can do that by just looking at when disasters happen, where they happen, and who they happen to. Right? And what type of event they are, I should say. Okay? And finally, our last goal is to think about decay. Okay? Decay of relationships over time. And if you think back to those two plots I showed, there was barely any decay. And I think that is really interesting preliminary result because it means that you can then capitalize on this increase of attention. Okay, so we've collected data for this nationally representative set of emergency management organizations on Twitter. We have snapshots of their personal networks at daily resolution for the past 4 or 5 years. Right, so really cool data. Here's just a look at what that raw data looks like. So here I'm just showing you the change in audience size, number of followers, right, personal network degree for these actors as a function of their size the previous day. So there's a lot of growth here, but the main point that I want to emphasize is highlighted with these sort of red points up here, right, orders of magnitude change in your network in just 24 hours. So we see that this happens a lot for local emergency responders. Right? Most of those points tend to be local organizations in the areas where disaster events happen. We know surprisingly little about how these emergency responders behave online. Right? And we know even less about their online audiences. Right? Who's paying attention to them? Can they stop the spread of misinformation or not? Right? Does what they post matter? How do people pay attention to and pass along their tweets? So these are the kinds of questions we're trying to explore in this project. And just to show you some preliminary results, we are studying the audiences of police precincts. Okay, so police accounts are often the first responders during crisis events. This data differs a little bit from some of our previous data, and it's starts in an offline way. Okay, so first thing we do is we think about a geographic region that we want to study. I'm going to show you Seattle, which shouldn't be a surprise, given I'm from Seattle. So we start in Seattle and we list all the police precincts, right? Ignoring Twitter for a second. Right? We don't really care about Twitter. That means we have a really well-defined population of users, right? Which doesn't often happen when you think about digital data. So we have a well-defined population of users. We go look to see which ones have Twitter accounts. We collect data about the location of where they're supposed to be serving, right, their beat, as we would call it, and the demographic characteristics of those constituents. Right? We use that with US Census data. We can estimate those things. And then we go to Twitter and we collect data about what they post and their follower graphs. Right? So their social networks on Twitter. Then we actually use geotagged tweets from their audience members to try to infer demographic characteristics about the online audience. Right? So if I see that your audience members post a lot of geotagged tweets in a particular location, I go look on the census about what the racial composition or demographic composition is in that area. Okay? So we have these time series of followers, we have census data, we have all sorts of different things here. So here is the network of police precincts in Seattle. And each one of these nodes is one of the beats, right? Seattle beat accounts. They each have individual accounts. And the big node down here is just the general Seattle PD account. So the nodes are connected here if they have significant overlap in their audiences. Right, so two nodes are connected, they share a lot of audience members. And what you see here is that if you're familiar with Seattle, there's a lot of geographic clustering. Right? So all these nodes up here are the northern Seattle neighborhoods. Then you sort of move into downtown, South Seattle, West Seattle. So not super surprising. But let's take a look at a couple. So here are two Seattle accounts. They correspond to neighborhoods in Seattle. One of them is in North Seattle, sort of the Wallingford area. The other one's in South Seattle, in sort of Columbia City, if you know Seattle, or have been to visit either of those places. Right? Wallingford, sort of northern Seattle neighborhoods are very not racially diverse. Right? And the ones in South Seattle are much more racially diverse. Okay. So here's what we do. We compare the estimated racial composition of the online audience with the populations that are served by these precincts. Okay, so in this plot, the orange bars represent the racial characteristics of the population that is served by these police accounts. Okay? And the blue bars represent the estimated racial composition of the online audience for those same police accounts. So a higher blue bar here means that compared with the offline demographics, right, that a particular racial group is much more overrepresented on Twitter. Right? And the flip is the other way around. Right, so what we see is really interesting differences. Okay? This is the predominantly white neighborhood in Seattle. We see that actually some of these non-white groups are overrepresented in the Twitter audience. This is the really more racially diverse neighborhood of Seattle, right? We see that whites are much more likely to follow that police account on Twitter. Okay, so let's just say, for the sake of argument, that the Seattle Police Department decides all crisis communication is going to be via Twitter. What would that mean? Right? It would mean that we have systematic inequality in information access and exposure. Right? And it would also mean that when crisis events happen, we would likely see differences in disaster outcomes, like survival or long-term well-being, that were even more exaggerated between these racial groups. Right? We already know they're exaggerated, right? Even more exaggerated because they have differential access to information. So luckily, this is unlikely to happen. But evidence really suggests that these kind of drastic changes in personal network structure exist, right? And they're not that uncommon. So I think there's really interesting theoretical and practical implications of this kind of mass convergence behavior. And we see that emergency responders are often the target for this kind of attention. But we don't really understand the characteristics or the biases in the online audiences of these organizations. And we need to know more about them. So we want to think about how a better understanding of this convergence behavior can allow these organizations to make use of the opportunity and avoid the cost of attention. Okay, so I'm probably out of time for today, so let me just wrap up. Hopefully I've shown you a little bit about how digital data, digital traces, these digital footprints we leave online, can be valuable for understanding social behavior during crisis. They allow us to test theories in ways we just really couldn't do in the past. Okay? So we have to refine and extend our theories, but there's really interesting things to be learned. So this research agenda isn't cheap, right? What does it entail? It means we have to make use of qualitative methods, statistical and machine learning methods, text analysis, network analysis, right? All kinds of different methods. And it means we have to incorporate data from a lot of different sources, right? Not just social media data, but census data, interview data, all kinds of different things. And this is a sort of multi-method, multimodal approach, is I think what computational social science has to offer to help improve our understanding of social behavior during crisis events. All right, so this is a large project. Let me just quickly thank my collaborators. Right, I have a number of awesome colleagues who help with this work. We have a team of student researchers who also participate in these projects. And of course, we couldn't do it without our funders. So thank you.